Bioinformatics Micromodules, Neighbor Joining. In this module, we describe another distance-based method for phylogenetic tree reconstruction. Recall that in the previous module, we described the UPGMA method, which merges the two closest clusters in every step. There are two potential problems with this approach. First, sometimes there are several cluster pairs with similar distance values, and it is hard to know which pair should be merged first. Once the decision is made, to a certain extent arbitrarily, the decision cannot be reversed, even if the merge is found to be a bad one later. The second problem is that when the tree is not additive, UPGMA does not have a systematic way to assign suitable branch names. This time, we introduce another distance-based method called neighbor joining that deals with these problems. It is also an iterative algorithm that merges two clusters at a time. However, unlike UPGMA, neighbor joining considers not only how close two clusters are when deciding which pair to merge, but also how far the merging clusters are from other clusters. We use U to denote the total distance from a cluster to all other clusters. Neighbor joining prefers to merge two clusters that are close to each other but far away from other clusters. In other words, it is preferable to merge clusters Ci and Cj if the distance between them, dCi-Cj, is small, but UCi and UCj are large. The rationale is that if the two merging clusters are far away from other clusters, we probably would not regret merging them later, since they would be merged with each other sooner or later, since they are so far away from other clusters. Putting these two objectives together, we define a scoring function called Q, where the Q score for clusters Ci and Cj is equal to the distance between them times the scaling factor minus UCi and UCj. The scaling factor is chosen to be R-2, where R is the current number of clusters before the merge. Why do we need this scaling factor? It is because UCi and UCj are sums over all other clusters, which can be much larger than the distance between Ci and Cj. If the scaling factor is not added, the scoring function would be dominated by UCi and UCj, which may lead to, for example, the merging of two outlier clusters that are far away from all other clusters but themselves also not close to each other. After understanding the scoring function Q, we are now ready to discuss the whole neighbor joining algorithm. At the beginning, each sequence forms a cluster by itself, but unlike UPGMA, these clusters are all connected to a central node called a hub. Next, we compute the Q score for each pair of clusters and identify the pair with the most negative Q score to merge. Here, when we say merging two clusters, the way to do it is to form a new node that connects it to the merging clusters and to the hub. Neighbor joining provides formulas for computing the lengths of the two branches that connects the new node to the two merging clusters. It also has a formula for updating the distance between this new cluster and each other cluster. These formulas may look complicated. We will explain how they are derived after seeing a complete example of neighbor joining. Finally, the Q scores are computed for the new cluster, and the pair with the most negative Q score will be merged, and this process is repeated again and again until all clusters have been merged. Notice that the final result of neighbor joining is an unrooted tree with the root position not defined. At the end of this module, we will discuss how the root position could be determined if we need it. Let's see a complete example. Here we have four sequences with their pairwise distances already computed. This distance matrix is the same as the one we saw in the first example of the UPGMA module, except that instead of having 5 input sequences, we only consider 4 here to make it simpler. According to the neighbor joining algorithm, the first step is to compute the Q scores. To do it, let's first compute all the U values, which are the total distances from each cluster to all other clusters. For example, UA is equal to the sum of the row for sequence A in the distance matrix, which is 8 plus 4 plus 6, which is 18. With this U vector ready, we can then compute the Q scores. The formula for the Q score is shown again as a reminder. Based on this formula, the Q score matrix can be computed. For example, the Q score for A and B is equal to the distance between them times the number of clusters minus 2, and then subtract from it UA and UB. The actual value is therefore 8 times 2 minus 18 minus 24, which is minus 26. The other entries of the Q-score matrix can be computed in a similar way. Now, looking at the Q-score matrix, the most negative value is minus 28 for the pair AC and also the pair BD. We can choose either of them to merge. Let's say we arbitrarily pick AC to merge. Then, as mentioned, a new node is formed, and it is connected to A, to C, and to the hub. Based on the formulas given previously, the distance from A to this new node is found to be 2, and the distance from C to this new node is also 2. We also update the distance matrix by computing the distance between this new cluster AC with B and with D, using the formula given previously. Now we again compute the U values and then the Q scores. This time, all the non-diagonal entries have the same score, and we can merge any two clusters. Suppose we decide to merge cluster AC and cluster B. What we do is to create a new node, which is connected to the node that represents A and C, to the node that represents B, and to the hub. Now we can also compute the branch lengths according to the formulas. Finally, we can update the distance matrix one more time, and then the U vector. Since we only have two clusters left, we may simply remove the hub to finish the whole process. If we compare the tree obtained from UPGMA and the tree we obtained from neighbor joining, we see that for this example, the two trees are essentially the same, except that the former is a rooted tree and the latter is an unrooted tree. However, please note that in general, there is no guarantee that the resulting trees of the two methods are the same. Now, let's go back to understand how the complicated formulas for branch lengths and cluster distances are derived. Suppose we want to merge clusters Ci and Cj, and we will connect them to a new node called Ck, which is in turn connected to everything else. We want to determine three values, namely the distance between Ci and Ck, denoted by x, the distance between Cj and Ck, denoted by y, and the distance between this new cluster to everything else on average, denoted by z. We want to set up equations to solve the values of these three variables. First, x plus z should be the average distance between x and other clusters not including Cj. Therefore, it should be UCi minus dCi_Cj divided by R minus 2. This division of R minus 2 is because not including Ci and Cj, there are R minus 2 other clusters. In the same way, we can set up an equation for y plus z. Finally, x plus y should be the distance between x and y in the original distance matrix. Therefore, we have three equations and three variables. We can easily find out the formulas for x and y, which are the same as the ones we showed before. This scheme helps determine branch lengths in a reasonable way even if the tree is not additive. Now, suppose we have another cluster CL, and we want to compute the distance between CL and the new cluster CK. If we look at the picture carefully, we see that the distance between CL and CK is equal to the distance between CL and Ci plus the distance between CL and Cj minus the distance between Ci and Cj. And then this whole formula is divided by 2. All three complicated formulas we saw now have been explained. Since neighbor joining gives an unrooted tree as the final result, what can we do if we want to find the root position? There are several common methods. The first method is to use something called an outgroup, which is a sequence that is known to have diverged first from all the other sequences. For example, suppose we have fly, pufferfish, mouse, and human. It is known that fly diverged from the other three first, and therefore the root position must be somewhere on the branch that connects fly to the other species. The second method is to look at the branch lengths and try to find a point that has equal distance to all the leaf nodes. The third method is to use knowledge about gene duplication. For example, if there are two paralogs of a gene denoted as alpha and beta, where the gene duplication happened before the divergence of two species, then the alpha homolog of the gene in both species should form a cluster before joining the cluster of the beta homolog. Before ending this module, let's have the final discussion of phylogenetic tree reconstruction methods. We have studied maximum parsimony, maximum likelihood, UPGMA, and neighbor joining. There are also other methods that we did not cover. Given the many choices, which method should we actually use? The simple answer is, there is not a definite answer. Which method to use in each study depends on the needs of the study. However, there are some general considerations that could be useful when deciding which method to use. Methods that do not rely on very strong assumptions are usually better. Methods that would not give dramatically different results when the inputs just change a little bit are also better. These can be achieved by combining the results of multiple trees using different parameter values or different subsets of sequences, or by using a formal probabilistic framework. Computational efficiency is also a consideration. It would be good to select a method that performs very well based on the main criteria that you care most and performs reasonably based on the other criteria.